The number systems for computers is our topic of today. And in computers, the numeral system is based on the binary numbers. And when we think about binary numbers, we think about zeros and the ones. And based on that information, we want to look at a few terms with what we call the byte, which is a binary digit. A single binary digit is a bit. It can be either a 0 or a 1. And then we have a byte. A byte is a combination of 8 bits, and I can give you an example. That is an example of a byte. And then the third one is a word, a combination. So a word is a combination of any number of bits. So this is a word. This could also be a word. And you can think of many other examples. And so the first one is a binary numbers. And basically they are only represented as zeros and 1. And so we say binary numbers are numbers to base 2. The second set of numbers is what we call decimal numbers. These are the normal numbers that we are familiar with, and these are to base 10. And then the third is the octal to base 8. And then the last one is the hexadecimal to base 16. And that is important, particularly for us to be able to deal with these numbers. So I want to give you a table that shows an example of these 4 types of numbers that we can use when we are representing or when we have the number system for computers. We have a table where we have the binary numbers, the decimal numbers, the hexadecimal, and the octal numbers. The decimal numbers are the numbers that we are familiar with, 0, 1, 2, 3, and so on. Now, how does the binary number comes about? That is what we are going to see. Then we have the hexadecimal and the octals. When you look at the octals, they start from 0, 1, 2 until 7. Then they start from 10, 11, 12. We are going to see how that comes about. For the hexadecimal numbers, they start from 0 to 9. Then from 10, we have letters. We have the alphabet, A, B, C, D, E, and then we also have the F appearing there. So we are going to find out how to convert from decimals to binary, and then from binary to other forms. So we are going to is that the binary numbers are to base 2. Starting from your right hand side, it's normally 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, 2 to power 4, 2 to power 5, and the list goes on. So for example, this, whenever there is a 0, it means that that bit is turned off. That means that value will be automatically be equals to 0. So it's 1 times 2 to power 0 plus 0 times 2 to power 1 plus 1 times 2 to power 2. And this gives us 1 plus 0 plus 4, which will give me 5 to base 10. Therefore, 1, 0, 1 to base 2 will be equals to 5 to base 10. Our last example. For example, I have numbers like 1, 1, 1, 0, 0. So this is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, and 2 to power 4. The first two on my right hand side are zeros, so they will not contribute anything. So definitely this one will be 0, this one will be 0, this one will be 4, this one will be 8, and that one will be 16. And that will give me 28 to base 10. So that binary number to base 2 is equals to 28 to base 10. We go back to the table that we had, and you look at a number like 13 to base 10. We are told that the 13 to base 10 is 1101. But is that true? This is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3. So if you go to that table, we are told that the binary equivalent of 13 decimal is 1, this is 0, this is 4, and this is 8. Because it's 2 to power 3 times 1. 2 to power 3 is 8, 8 times 1 is 8. 2 to power 2 is 4, 4 times 1 is 4. 2 to power 0 is 1, 1 times 1 is 1. And when you look at this, it becomes 13 to base 10, which is also equals to 0, 1, 2 to base 2, which is our binary number. I'll give you an example of numbers. So I'll give you a number that is converted into octal. So basically what you have is 1, and then you have, if you wish, you can put zeros on that. Zeros will not change anything. So we are treating this as two different numbers: 2 to power 0, 2 to power 1, 2 to power 2, then 2 to power 0, 2 to power 1, 2 to power 2. And we know on this side it will be 1, and on this side it will be 4 plus 1, this is 4, this is 0, and this is 1, and that is 5. So this will be 15 to base 8 is the same as 1102 to base 2. So you it in a way that I can separate them. So for example, if I add that, I'll just create them up. So those are my numbers to base 2. So I'll put in a 0 here. This is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 0, 2 to power 1, and 2 to power 2. 2 to power 1 times 1 is 2. Everything else is 0. So this is 4 plus 2 is 6 plus 1 is 7. So 0, 1, 0, 1, 1, 1, 2 is equals to 27 to base 8. So that's that. So what I do is this will be alone. Then I have 1, 0, 0. Then I have 1, 1, 0. So this is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 0. If you wish, you can add more zeros on this side. They will not change the outcome because zeros are switched off. They will not contribute to the answer. And therefore, this will have three numbers because the first one is 1. The first box here is 1. This box here gives me 4. And this box here gives me 6. This is 4 plus 2, which is 6. So it is 146 to base 8. And I divide the bits in groups of 4, starting from right hand side. And so this one is divided in this format. So this one is 1. This is 2 to power 0, 2 to power 1, 2 power 2, 2 power 3. This is 8, 10, this is 11. We say that our numbers will be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we have A, B, C, D, E, and F. So this is like our 10, this is like our 11. So this becomes 1B to base 16. So this, the hexa equivalent is 1, B, because this is 11, which is a B, to 16. 1, 2, 3, 4. 1, 2, 3, 4. And I want to convert it to hexadecimal. The procedure is the same again. I separate it into 4 bits. There are 8, so it will be straightforward. This is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3. And we know this is already 2 to power 3 is 8, 8 plus 4 is 12, plus 1, 13. That is 13. And this is 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, 8, 10. This is 14. And if you look keenly, 12, 13, 14. 14 is E and 13 is D. So the hexadecimal equivalent of that is ED16. And I have an example of a number. Like I have a number like 23 to base 8. So what we do is we separate this into bits. So what is 2? Remember, it's 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3. So this is 1, 2, 4, 8. I look for a combination of numbers that gives me 2. On this side, the numbers, the combination is 1 and 0. Remember, octal, we have to have them in groups of 3. That's what we said about the octal. It must be in groups of 3 for us to work with. So the number 2 is I switch on this second one here and I switch off this, and then I put a 0 here because they must be in groups of 3. Now 3 is represented by 1 and 2. 1 and 2. So this one will be on, this one will be on, and this one will be off because it will be 1 plus 2, that gives me 3. Therefore, the binary equivalent, I don't need 0 on the left hand side, so I'll just say it's 10, 0, 1, 1. And that is the binary equivalent of 23 octal number. 4, 2, 1, for example. And what makes 4? 4 is 1 and 0, 0. This is 2 to power 0, 2 to power 1, 2 to power 2. 2 to power 2 is 4. So that is 4. What makes 2? The number here should be 1. So 0, 1, 0. So this is a 2 because everything else is off. 2 to power 0, 2 to power 1 is 2. So that makes 2. What makes 1? The first number must be a 1. The others can be zeros. So this is 1. This is 2. And this is 4. The binary equivalent is then 0, 0, 1 to base 2. So now we can move from octal to binary. We can also do A. Remember, hexadecimal, it should be groups of 4. And if we keep that in mind, then it becomes easier. So what represents 2? 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, 1, 2, 4, 8. Which numbers here will give me a 2? 4 of them. It's a 0, 0, 1, and 0. It's only this number that is active here, and that will give me a 2. Remember, what is A? We have said it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So this is A, this is B, this is C, and D. And then we have the E and F. The E and F. So it gives me a 10 here. It is a 8 and a 2. A 8, 4 is 0, a 2 is a 1, and that is a 1. So 1, 0, 1, 0 will give me the letter A. A to base 16 is equals to 1, 0, 10, 10, to base 2. I don't need to put the zeros on my left hand side. Remember, our B is 11 and our numbers is 1, 2, 4, 8, 16. So which numbers will give me 11? It is 8, 2 and 1. So I'll have 1, 0, 1, 1. That is for B. And C is 12. What gives me 12? And it's 8 and 4. It's 1, 1 and the others are 0. So the binary equivalent of BC is that. So now we have been able to move from hexadecimal to the binary number equivalent. 12 to base 10. We want to move to binary. So what I have is I have the number, I have the base, I have the results, I have the remainder, and the remainder is also my binary number. So for example, my number is 12. 12 divided by 2, which is the base of the binary, is 6. And 12 divided by 2 is 6, remainder 0. So here I'm left with 6. 6 divided by 2 is 3, remainder 0. Then I'm left with 3. 3 divided by 2 is 1, remainder 1. And then 1 divided by 2 is 0, remainder 1. So that is the number that we have if we divide through using that process. And then our numbers, we lead them from down going up. So therefore I can say 12 to base 10 will be equals to 1100 to base 2. Number, we have the base, then we have the result, we have the remainder, and the remainder in this case is the binary number that you're interested with. So let's think of a number maybe like 31. So 31 divided by 2 is 15, remainder 1. 15 divided by 2, which is the base for the binary, is 7, remainder 1. 7 divided by 2 is 3, remainder 1. And 3 divided by 2 is 1, remainder 1. And 1 divided by 2 is 0, remainder 1. Therefore, that 1 to base 10 should be equals to 1, 2, 3, 4, 5 numbers. Method, for example, if I have a number like 40 to base 8, what I prefer doing is I prefer first of all, so which numbers? 1, 2, 4, 8, 16, that 2. This is 1 and 1. That 2 plus 8 is 40. Everything else is a 0. So the binary equivalent is that. Because I want to move from a number that is octal to hexadecimal, then I can take this number and separate it into 4 bits. This is 1, 2, 4, 8. So this is 2, 8 is equals to 8 to base 16. You remember, for you to use binary to hexa, you have groups of 4. And then from octal, so it is octal to binary, and then from binary to hexa. So if 25 to base 10, first of all I'll move to decimals, to binary. I would move to binary. 1, 2, 4, 8, 16. 32. So which combination of numbers? It can be 32, so it is 16 is one of them. If I put 8, it gives me 24, then I have 1 that gives me 25. So I get the binary equivalent. So I move from decimal to the binary equivalent, and then from the binary, now I can move to octal. So this is 1, and this is 1 and 2, this is 3, and that is 31 to base 10. I'm sure you've loved this video. So if you have, click the subscribe button, and thank you for watching.